Welcome to the lesson 36 of industrial instrumentation. This lesson is a continuation of the lesson 35 where we have discussed the chromatography 1. In this lesson we will discuss chromatography 2. So, let us look at the contents. This is a chromatography 2 as I told you. The contents are gas chromatography, liquid chromatography, chromatogram. Okay, so we will see that in this particular lesson, so we will discuss how the chromatogram should look like, and what are the, if there are multiple peaks comes, and what are the problems, what exactly the shape of the chromatogram should be. I mean that depends finding the concentrations of the different components of the gas and liquids precisely. At the end of the lesson or end of the chapter, the viewer will know different equipments and different operation techniques used in gas and liquid chromatography, different detectors used in the chromatography and their purpose and their classification. We will find there are different types of detectors available. There are thermal conductivity detector, there are flame ionization detector, there are electron capture detector. So, there are different, the principles are somewhat different, though the thermal conductivity detectors are the oldest one and most widely used detectors in the gas chromatography. But we will discuss the other detectors also, where you will find that we will making a derivatives of the particular element of the mixture, so that to find the concentration accurately. How do operating conditions like pH value, temperature affect the chromatogram? Okay, so we will find these things also, the pH value, though it's not very important in the case of gas chromatography. This is very important in the case of liquid chromatography. Gas chromatography, already that we have discussed. Gas chromatography makes use of a pressurized gas cylinder and a carrier gas such as helium, which is inert in nature, to carry the solute through the column, because we will find, we have discussed this thing, that there is a column and through column the gas should flow, right, and there is a packing material inside the column. So, which will adsorb or absorb and elute it after some time one by one. Gas adsorptions, that is gas solid chromatography, involves a packed plate comprised of an adsorbent used as a stationary phase. Common adsorbents are zeolites, silica gel and activated alumina. These are the most common sort of adsorbents are used in the chromatography. This method is mainly used for separating mixture of gases. So, you will find this is basically used for the mixture of gases, right. Gas liquid chromatography is a more common type of analytical gas chromatography. In this type of column, an inert porous solid is coated with a viscous liquid which acts as a stationary phase, and diatomaceous earth is the most common solid used, and solutes in the feed stream dissolve into the liquid phase and eventually vaporize, and the separation is thus based on the relative volatilities. Okay. So, you can see that these are all different. This already we have discussed in the lesson 35. Now, we are discussing in more details. Okay. You see the last line, which is most important. The separation is thus based on the relative volatilities. Okay. Now, capillary gas chromatography uses a glass or fused silica capillary walls, which are coated with an absorbent or other solvent, and the column has only limited capacity because of the small amount of stationary phase. However, this method also yields rapid separation of the mixtures, right. Now, chromatographic equipments, what we need and the entire chromatographic equipment, let us look at that. Basically, you will see the figure in the next diagram, in the next slide. Basically, a gas chromatograph consists of 6 parts: a supply of carrier gas in a high pressure cylinder, a sample injection system. Number 3 is the separation column, okay, where we have the packing materials and all those things. The detector, which is most important. In these particular lessons, we will discuss the detectors in very much details. Okay. There are various kinds of detectors. We will discuss the detectors in already we have discussed about the the packing materials in the case of gas chromatography. We will discuss also some to some extent that thing in this particular lesson. An electrometer, that means, and a separate thermostated compartments for housing the column and detector, so as to regulate their temperatures, right. So, detector usually followed by a strip chart recorders or any other electronic recorders, where we will record the peak. In the strip chart recorders, you will get a hard copies, it can be computerized also, where you will get the actual plot on the screen itself. Now, see, this is the schematic of a gas chromatograph. We can see here, okay, these are sample injection systems. We have a column here, you see the columns are made like this, okay, these are the columns, okay, these are the columns, we can see here, these are the columns. Then it is going out, and this entire thing placed in a thermal chamber. You can see these are thermostatic chambers we have used, and there is a bridge. What is the bridge? And there is a reference detector. We will find that to make the other things nullified, because you see this type of measurements already we have did in the case of Wheatstone bridge. We will find the same principles is utilized, especially in the case of thermal conductivity detector. This is used, and we have a measuring detectors and we have a recorder. This is a reference detectors. Okay, this has no column, nothing is there, only detector is there, and there is a measuring detector, because measuring detector, suppose the detector, if it is temperature, if I want to make the temperature independent or ambient temperature variation independent, so in that case I should use a reference detector. Reference detector has no column, nothing, but it has the same same material, same what are the inside the components, so that the temperature variation everything will be nullified, and I will get the only the this will go to the two opposite arms of the Wheatstone bridge, so that it will be nullified. We will see this thing in the next, in subsequent slides. Now, sample injection systems, let us look at. The sample must be introduced as a vapor in the smallest possible volume. Sample should be very small. So, small is the small is the amount that is better for our detection. The peak will be better, that is most important thing, right. So, the sample should be, because ultimately we are measuring the relative concentrations, okay. So, it does not matter, if it is small or large. So, if it is small, so it is good for us, okay. The detection will be easy, the peak will be more separable, we will see that type of things. The sample must be introduced as a vapor in the smallest possible volume and in a minimum of time without decomposition. It should not be decomposed, that is most important thing. Liquid samples, its order of 1 to 10 microliters in a volume are usually injected by a micro syringe through the self-sealing silicon rubber septum. Okay. So, it is a very small amount that we can see 1 to 10 microliters, and it should have a micro syringe, so that a very small amount can be injected. The most accurate and precise method for the gas sample used a calibrated sample loop of 0.5 to 10 milliliters and a multi-port rotary valve. So, different types of rotary valves will be used in the case of this type of sample injections, okay, because sometimes we need a valve, so that the precise amount can be injected. The smaller the sample, the better the peak shape, that I told you, okay. The peak shape should be better and better. How the peak should look like, let us look at that. You see, the peak should be, the ideal peak should be, suppose I have two components, so time it is in 1, 2, 3, 4. So, it is coming like this, the two peak is coming like this, right. It is a good separation of the two components, the two peaks are coming like this. It might be sharp also, it may not necessarily it will be like this one, it can be sharp also, it can be like this one, it can be very sharp like this one also, okay. Now, if this is always possible if the sample quantity is very small. If the sample quantity is large, you can see that the what type of peak you will get. You may get a peak which looks like this, actually looks like this one. So, it is very difficult to find the area under the curve from this graph. So, this is the other way why we give so much emphasis on the small quantity of the sample, right. The smaller the sample, the better the peak shape. When a very dilute solutions are to be analyzed, the use of a concentration curriculum such as 2,6-diphenyl p-phenylene oxide porous polymers allows the quantitative transfer of up to 20 microliter of sample. Okay. So, this is a precise transfer of the particular amount of liquids we are considering here. Now, derivative formations. Derivative play an important role in gas chromatography for analysis of polar compounds such as fatty acids, steroids, drugs, biological amine and phenols, etc. Derivatives make a polar compound less polar, improve quantitations and increase the volatility of high molecular weight compounds. Chromatographic columns. So, let us look at the columns first. There are basically two types of columns, the packed bed column, open tubular or capillary column. That is already we have discussed in the lesson 35. The packed columns are made of stainless steel, copper or glass tubing of diameter 1.6 to 9 millimeter and typically is 3 meter in length. Okay. We have seen that it is a zigzag fashion because it is a large column length, 3 meter of length, you can see you cannot accommodate. So, it should be zigzag face. Capillary columns have an open unrestricted path for the carrier gas within the column, and it is a long narrow tubing of length 50 to 150 meters, extremely long, and of diameter 0.25 millimeter, extremely small, and its inner wall is coated with the liquid stationary phase to about 1 micron thickness, right. Column constructed of silent treated Pyrex glass have the most desirable features. A good packed bed column will have a nominally 1000 to 3000 plates per meter. We have seen that this concept actually came from the distillation columns. So, more number of plates, better is the separation. Capillary columns range from 1000 to 4000 plates per meter. This is a theoretical value, right. The sample capacity of capillary column is determined principally by the thickness of the stationary phase on the column walls. The coating usually done is of silicon gum. Packed columns are usually formed into several coils and placed within the open compartments. Okay, it is a several coils we have seen. Okay, its coil looks like this, that we have seen. It looks like this, right? Looks like this. It can be coil like this one also, but it is better. If you have, so it will come and it will go out like this one. So, the packing materials are inside this column. So, the packed columns are usually formed into several coils and placed within the open compartment. Open compartment is nothing but a temperature, is a thermostat based or more precisely controlled temperature environments. Capillary columns have tubing coil into an open spiral and basket coil or a flat pancake shape. Supports. The purpose of the support is to provide an inert surface onto which the stationary liquid phase can be placed in a packed column. The diatomaceous earth supports may be either fire brick derived materials like chromazole P and anachrome ABS, etc. These special materials. The acid washed grade will perform quite well for the analysis of relatively non-polar samples. Liquid phase. The stationary liquid phase provides the separation of the column. In addition to selectivity, the liquid phase should be chemically or thermally stable, that is most important thing. Now, ovens, as I told you, the oven is used for maintaining the precise temperature control around the column. Okay. Hence, the column oven should be free from the influence of changing the ambient temperature and should have a well designed and adequate airflow system. There should be good airflow systems, otherwise temperature control will be difficult. Detectors. Now, detectors we will discuss in very much details, as I told you. The detector senses the presence of the individual components as they leave the column as they leave the column. So, we will have the, so all the detectors, we have injection systems, we have a carrier gas, okay, we have a solvent pump, everything is there. So, it will go to the column, from the columns it will come out, it will elute depending on the absorbent material, and ultimately it is come to the detector. So, all the columns will be followed by detector, and detector will be followed by another recorder. The detector output after amplification is traced on a recorder, as I told you, right. The different types of detectors generally used are thermal conductivity detectors, flame ionization detectors, thermionic emission detector, flame photometric detector, electron capture detector, and helium detector. So, we will discuss some of the things, okay. So, we will discuss some, not all we will discuss in this case. So, that anybody can refer to some standard book on the gas chromatography for this. Detectors in chromatography are generally operated in two different ways. They respond either to the concentration of the solute or the mass flow rate. Those responding to the concentration yield a signal which is proportional to the solute concentration, which traverses the detector. An Aleutian peak will result when the signal is plotted against time, right. So, there can be different components. So, how does it look? Let us look at, you see here that the selectivity efficiency, this is very important in the case of the peak, right. So, those are the things we should discuss. What is the selectivity, what is the efficiency? Let us look at. I have, you see here, these are injections I have made here. This is adequate selectivity, but poor efficiency. You see here, good efficiency and selectivity. This is the desired characteristics and selectivity. Okay. And you see this is another one where you can see like this one. This is a good efficiency but poor selectivity. Okay. So, selectivity, efficiency, I mean everything we have discussed for the two columns in this particular slide, right. So, these are the desired characteristics for any, I mean the peak should be look like this one. So, who will decide this one? Actually, this will be decided in the detector itself, efficiency of the detector, selectivity of the detector. So, the two most important thing for the detector is the selectivity and efficiency, and also the partition ratio, right. So, an Aleutian peak that I just drawn, Aleutian peak, the peak is the what we have drawn is called the Aleutian peak, right. So, this is the peak which we have drawn, talked about. So, this is the suppose. So, this peak is called the Aleutian peak because it will come out of the gas and suddenly it will detect at the output. For such detectors, the area under the peak is proportional to the mass of a component and inversely proportional to the flow rate of the mobile phase. Hence, an important care of keeping the flow of the mobile phase constant for such detector is necessary. If differential detectors that responds to the mass flow rate, the peak area is directly proportional to the total mass and there is no dependency on flow rate of the mobile phase. You see, let us go back first of all. Now, you see when I talked about the Thermal conductivity detector. Thermal conductivity detector is the one of the oldest detector and it still is used because of its simplicity of the system. It is very simple system and it is very widely used. Data are available over the years, people are using these things, and it is non-destructive. Okay, that is most important thing for the many of the gas chromatography, right. So, let us look at the how it looks. I have a block looks like this. Okay, let me take a new page. Block is there and okay, here actually I will put the detector. So, here it will look like this, then it will go like this. Okay. So, this is our block. So, this is the gas flow in, and this is the gas flow out. Okay. And this is the block. It will work as a heat sink, please note, work as a heat sink, because there is a some sort of heating here. And this actually, if I want to make it is independence of the detector, okay, independence of the other parameters of the detector, because detector output should be solely depends on the I mean different components of the or the Aleutian peak. So, in that type of cases it should not influence by any other I mean any other components of the detector itself. So, that is the reason we are using two detectors. So, let us look at how the two detectors methods are using. It looks like this. We have a one detector here, then we have a here 100 ohm, this is 100 ohm, bridge balance. So, there is an ammeter 0 to 500 milliampere. This is coming through a resistance 100 ohm. It is coming here. So, this is excitation voltage Ex, BJ excitation. So, this is coming to the recorder, because this is the unbalanced voltage. Okay. So, this is the detector 1, and this is the detector 2. Okay. So, same carrier gas is passing through both the detector. Okay. So, in both the cavity, that means cavity means actually we are showing that we can have a 4 same sensors also. Okay. So, it looks like this. You see, this is the thing. Let me first explain, then I will go to that. See, two detectors are there. So, same carrier gas is passing through both the detectors, but there is no column or anything on the detector 2. Initially, what we will do, I will balance with the by varying this potentiometer, I will balance the bridge. So, whenever the detector I mean the Aleutian peak comes, that means when the gas is coming out, I will have Aleutian peaks. So, detector output will change, because there is a thermal conductivity there. So, it will change. So, automatically if it changes, I will get an unbalanced voltage that will be recorded in the recorder, right. Now, again you see in the hydrogen flame ionization detectors, for high sensitivity analysis of organic compounds, the hydrogen flame ionization detector is used. That is different things. Okay, we will discuss that thing also. So, two detectors are using. You see, we can have 4 detectors also, 4 detectors in one block itself, right. It looks like this. You see. So, what we have 4 detectors is a block. I can have 2 detectors and I can have 4 detectors also. it is coming like this one, right. Okay, let us go back. Now, you see this is the flame ionization detectors. As I told you, this flame ionization detector is one of the detectors. So, the different components in the flame ionization detectors. This is the exit end of the column. Let us look at. You see here a jet capillary is there. Okay. It is flown through this one. This is the hydrogen air flame, and air is coming through this one, and this is with the air and hydrogens. It is so we have a collector assembly nut, we have insulators, and we have a collector roll. We are putting across the high voltage inside the detector plates. So, what is this? Let us explain. The flame ionization detectors is currently one of the most popular detectors because of its high sensitivity, wide range, and great reliability. As shown in the figures, this particular figure, figure 2, I think, figure 2, the column effluent enters the burner base through the multiport filter. So, through this one it is enters and is mixed with the hydrogen gas, and mixture burns at the tip. This is the tip of the hydrogen, you see this is the tip. Let me okay. So, this is the tip, you can see here, this is our tip, hydrogen tip. The jet air with air or oxygen, because through air it is coming, so it is going down and is burning. Ions and the free electrons are formed in the flame, and these enter the gap between the two electrodes. We have two electrodes, and there is a high voltage and the flame jet and the collector, which may be a parallel plate or might be cylindrical. Okay. Now, this is mounted around 0.5 to 1 centimeter, 1 centimeter above the flame tip. So, above the around 0.5, either to 0.5 to 1 centimeter, half centimeter to 1 centimeter above the flame tip, and across the two electrodes a high voltage of 400 volt is applied, right, and this lowers the resistance across the gap and causes a current to flow, right. Normally, an external bucking voltage is produced to balance the potential generated by the ions and free electrons generated in the pure hydrogen air flame. This ensures that a net current flows only when ionized materials enters the gap. When the net current flows when the ionized materials enters the gap, thus enhancing the differential sensitivity of the detector. The current flow across the external resistor is sensed with the voltage drop and is amplified and displayed on a recorder. Now, hydrocarbon groups are introduced into the flame, and a complex process takes place in which positively charged carbon species and electrons are formed. Now, the current is greatly increased. Okay. Now, this flame ionization detector responds only to the substance that produce charged ions when burned in a hydrogen air flame. So, that is most important thing. In an organic compound, the response is proportional to the number of oxidizable carbon atoms. So, this is basic principles of the flame ionization detector. Now, if I look at the thermionic emission detector, you see this is thermionic emission detector. It is principally something different. It employs a fuel poor hydrogen plasma. This low temperature source suppresses the normal flame ionization response of a compounds not containing hydrogen and phosphorus. Although the response to carbon is not entirely eliminated, a non-volatile rubidium silicate bead, here you see here non-volatile rubidium silicon bead centered about 1.2 centimeter above the plasma jet is electrically heated by variable current supply to between 600 to 800 degree centigrade. This arrangement permits the fine adjustments of the bead's temperature and independent of the plasma as a source of thermal energy. With a very small hydrogen flow, the detector responds to both nitrogen and phosphorus compounds, and enlarging the plasma, the changing the polarity between the plasma tip and the collector, and detector responds only to the phosphorus compounds. Okay, so that I can make it nitrogen, I can make it sensitive to the phosphorus compounds also. Now, compared with the flame ionization detector, the thermal emission detector, thermionic emission detector is about 50 times more sensitive for nitrogen, okay, and about 500 times more sensitive for phosphorus. Okay. So, any traces of phosphorus, any traces of nitrogens can be better detected in the case of thermionic emission detector compared to the flame ionization detectors, though flame ionization detectors also is a comparatively new compared to the thermal conductivity detector. The minimum detectable limit is around 0.06 pg per second for nitrogen. Okay. So, this is the thing you can see here, that there is a flame tip which is around 1.27 above the plasma jet. Okay. So, this is our thermionic emission detector. Last we will discuss the electron capture detector. You see, this is the electron capture detector. Now, electron capture detector has two electrodes within with the column effluent passing between. One of the electrodes is treated with radioisotopes that emits high energy electrons as it decays, and these emitted electrons produce large amount of low energy thermal secondary electrons in the gas chromatography carrier gas, all of which are collected by other positively polarized electrode, either of the positive polarized electrode. Molecules that have an affinity for thermal electrons capture electrons as they pass between the electrodes and reduce the steady state current, thus providing an electrical reproductions of the gas chromatography peak. Of the two general designs, the plain parallel and the concentric cell, and the latter design is preferred, since it is easier to construct a small low loaded volume cell in this form. Now, particular radioactive sources which are used, that the tritium adsorbed in the titanium or scandium, and nickel 63 as a foil or plated on the interior of the cathode chamber. Tritium sources have a high specific activity, giving a large standing current and a high sensitivity, but the beta energy is so low that the source is extremely susceptible to contamination. The maximum working temperature is 225 degree centigrade. Now, nickel 63 is a higher energy sources and can be used up to 400 degree centigrade. Okay. So, this you see, this is the we are talking about the electron capture detectors. Let us now go back. Now, adsorbent in cases of gas solid chromatography. Inorganic molecular sieves are naturally occurring for synthetic or synthetic zeolites, which are comprised of interconnected cavities or pores of uniform size. 4 types of molecular sieves are varying in pore diameters. Okay, this is adsorbent because this is different types. So, the dimensions of the pores are so that the it is Armstrong level, so that the some of the larger cannot enter the pores, some will enter, which is smaller in diameter. Varying pore diameter and alkali metals contents are available. Type 3A, a potassium aluminosilicate with the pore diameters of 3 Armstrong. It will adsorb the molecules such as water and ammonia. Okay, it will adsorb the molecules of water and ammonia. Type 4A, it is a sodium analog type of 3A. Okay, it will adsorb the molecules of carbon dioxide, right, sulfur dioxide, hydrogen, disulfide, ethane, ethylene, propylene and ethanol, right. Type 5A with calcium replacing part of the sodium content of type 4A, and it will separate most of the hydrocarbons. Okay. In many this petrochemical industry, this is very important. Type 13X, a sodium aluminosilicate of different crystalline structure from the preceding types, has a pore diameter of 10 Armstrong. The molecular sieves separate molecules not only according to the size and configuration, but according to the polarity and degree of unsaturation as well. Columns prepared from carbon molecule sieve type B with pore radius of 5 to 15 Armstrongs are also available. Porous polymer packings are analogous to the porous gels used in the exclusion chromatography. Those made from the copolymers of aromatic hydrocarbons provide column packings of low to moderate polarity. Polymers made from the acrylic esters and provide the packing of moderate to high polarity. Solid absorbents like silica gel, alumina etc. are used for specific applications, right. So, these are the some specific applications we will use, silica gels, alumina, etc. Right. It is also, these are also basically adsorbent, please note. The large retention of silica gel for carbon dioxide which elutes after an ethane is useful in multi-column systems, okay, because there is large retention, which is it will retain it for a longer time. So, it will obviously help to get a better peak. So, the large retention of the silica gel for carbon dioxide which elutes after ethane is useful in the multi-column system. Similarly, alumina is useful for retention of unsaturated hydrocarbons, because unsaturated hydrocarbons, so it is obviously helpful for retention, because we have to retain, right. So, that is the thing of the packing materials. Multi-column systems, gas solid chromatography is more complicated than the gas liquid chromatography, since all gas mixtures contain components which are not separated on or will not pass through a particular column in reasonable time. Back flushing substantially reduces the analysis time. In series cross detector, across detector, one column is used before the detector and a different column is used after the detector. The same packing may reside in both the columns. Okay. In two column series bypass techniques, a column switching valve enables a column 2 to bypass by the carrier gas and at the selected time, so that the certain components can be stored temporarily there, while the separations are made on column 1. Liquid chromatography, let us know only 15% of the known compounds lend themselves to the analysis by gas chromatography, owing to the insufficient volatility of thermal stability. This is the most important, the gas should not vaporize every time we have said, right. The liquid column chromatography does not leave the this limitation. The interchange or combination of the solvents can provide special selectivity effects that are absent when the mobile phase is a gas. Traditional liquid chromatography was achieved by gravity, hence analysis took place at a slow rate. In modern liquid chromatography, known as the high performance liquid chromatography, a pressure is applied to the column, forcing the mobile phase to through at a much higher rate, and the pressure is applied using a pumping system. So, okay. Instead of gravity, I am using a pumping system. You see, this is a typical liquid column chromatography, entire instrumentations we are showing here. Okay, we have a reflux systems we can see here. I am sorry. Okay, you see here. So, we have a pressure gauge here, we have filter, heated solvent reservoir, pump, and this is a preoculum, and this is the analytical column. So, we have injection head here, syringe, and there is a detector, and it is come to the detector. So, this is the entire instrumentation system. So, this thing should be put in a thermostatic bath, so that the constant temperature can be achieved, right. The general instrumentation for liquid chromatography incorporates a solvent reservoir for the mobile phase, a solvent pump, a preoculum except for the bonded phases, a pressure gauge, a sampling or injection device to introduce the sample into the column, the separation column, and a detector. Solvent delivery system. The solvent delivery system should have the following features: precise delivery of solvent over a relatively broad flow range, maximum pressure attainable, compatibility with other components in the high performance liquid chromatography system, compatibility with the wide choice of the solvents, and low noise levels in the detector resulting from any pulsations. Removal of the dissolved air and other gases is also necessary. Okay. So, there are three main types of delivery pumps used for solvent delivery system, namely reciprocating pumps, syringe type pumps, then constant pressure pumps. Final choice of pump is made after the considering whether the isolation of the gradient dilution is to be performed and the minimum detectability limit desired, type of separation column, the detector employed, precision in quantitation, and the cost of the package chromatograph. Sample introduction. The ideal sample introduction method should be able to insert reproducibly and conveniently a wide range of sample volumes into the pressurized column as a sharp plug with little loss of efficiency. Two kinds of sample introduction methods are mainly used. One is a syringe injection. In the syringe septum injection, a small 10 microliters, already we discussed, the smaller the amount better is the peak. sample is introduced into the pressurized column with a high pressure syringe through a self sealing elastomose septum and directly on the top of the column packing. Okay. So, it is to be given on the top of the column packings. We have seen that thing. If you look at the figures, you will find, you see syringe. So, it is at the top of the column packings we are giving here. You see here top of the column packing we are giving. Sample introduction. Right. Now, sampling valves and loops. Sampling valves allows the sample to be introduced reproducibly into a pressurized column without significant interruption of flow. Separation column. Heavy wall glass or stainless steel tubing which can withstand a high pressures are generally used to construct liquid chromatography columns. Columns with an internal diameter of 5 mm provide a good balance between the sample capacity, the amount of packing used, the solvent required and column efficiency. 2.1 mm bore packed column requires about 5 times the inlet pressure or as the same length of 4.6 mm bore column for the same flow rate. Replacing the steel columns with comparable cartridges permits the dedication of the cartridge to each application, thus maximizing the life. Column packing that lie in the range of 3 to 7 micrometer in diameter are used for exclusion chromatography. Column temperature is maintained by circulating air baths or by using water jackets or thermostats, that is already we have discussed. Oven is nothing but a thermostat where its constant temperature is maintained. Okay. Or we can make it, I mean instead of oven we can circulate with the jackets where the constant temperature, and you can by controlling the circulating waters we can control the temperatures of the oven also of the column. Preceding the separation, column should be short 5 cm protection column to adsorb or filter unwanted materials. We can see there in the, if you go back to the initial slide, you will find on the instrumentation systems we have a filter. Okay. So, this will be filter all the unabsorbed unwanted materials. Detectors. Choice of detectors mainly depends on the problem at hand. The different types of detectors used, we have photometric detectors, flowmetric detectors, infrared detectors, differential diffractometers. Types of high performance liquid chromatography methods. Adsorption chromatography. Adsorption chromatography is probably one of the oldest types of chromatography around. It utilizes a mobile liquid phase that is adsorbed onto the surface of a stationary solid phase. Equilibrium between the mobile and the stationary phase accounts for the separation of the different solutes. In this method, the components are separated on the basis of their polarities. Physical selectivity is dominant in adsorption chromatography. Adsorption chromatography is used when the sample is completely soluble in organic solvents and the molecular weight is less than 2000 for all the sample components. We have for more than 2000 we have some different methods. Liquid partition chromatography. This form of chromatography is passed on the thin film formed on the surface of a solid support by a liquid stationary phase. Clear? Solute equilibrates between the mobile phase and the stationary liquid. LLC is best used to separate homologues where the separation is based on the molecular weight selectivity, right. A successful separation is achieved by establishing the proper balance between the attraction of the mobile phase solvent and the stationary liquid phase for the sample. Good separation can be achieved by matching the polarity of the sample and the stationary phase and using a solvent which has a different polarity. Ion exchange chromatography. Here in this type of chromatography, the resin, the stationary solid phase is used to covalently attached anions or cations on it, right. Solute ions having opposite charge in the mobile liquid phase are attracted to the resin by electrostatic forces. right. This method is used for compounds with the ionic and ionizable functional groups. If the sample is the insoluble in organic solvents, but soluble in water, giving a solution that is not neutral or is only soluble in dilute acids or alkali, then ion exchange chromatography is used. Molecular exclusion chromatography, this is also known as exclusion chromatography. Sometimes it is a simple exclusion chromatography, but actually it is a molecular exclusion chromatography. Let us look at. It is also known as a gel permeation or gel filtration chromatography. This type of chromatography lacks an attractive interaction between the stationary phase and the solute. Sometimes there is desirable properties. It is generally used when the molecular weight approximately exceeds 2000. In case where it is less than 2000, we have adsorption method. Here we have a molecular exclusion gas chromatography, which is used for the molecular when the molecular weight is more than approximately exceeds 2000. This method is based on the Porous property of the substrate to sort and separate sample mixtures according to size. The pores are normally small and exclude the larger solute molecules, but allow smaller molecules to enter the gel, causing them to flow through the larger volume. This causes the larger molecules to pass through the column at a faster rate than the smaller ones, right. So, the pores are normally small and exclude the larger solute molecules, but allow smaller molecules to enter gel, causing them to flow through the larger volume. This causes the larger molecules to pass through the column at a faster rate than smaller ones. The chromatograph output, or which is called the chromatogram. So, let us look at. Consider the output from the detector, that is chromatogram as shown in figure 6. You see, this is a typical chromatograph which we got at the detectors or the strip chart recorders, or the different components. We have a gas, we have a components of A, B, C, D. Okay, this will be, I am sorry. So, this will be A, B, C, this will be D, different components, and this will be E, right. So, this is the chromatogram for the another one. So, is the adsorptions, this is also you see here. Since the sample is separated in the column, different peaks on the chromatograph corresponds to different components in the mixture. Clear? Since the sample is separated in the column itself, so when it is at either absorptions, it elutes and come to the detector. So, it is one by one is detected. Different peaks on the chromatogram corresponds to different components in the mixture. This I told you several times. The chromatograms were obtained by separating a protein mixture using ion exchange chromatography. Okay, depends on the what type of. So, in ion exchange chromatography, you can use a protein, you can separate a protein mixture. The separation corresponds to the chromatogram and was performed at a lower pH value than 1 in P. If you look at, you see the pH value is was performed in a lower value in A than B. A has a lower pH value than B. You see, obviously the separation is better in the A. So, this will tell you that actually how the pH will affect the actually my chromatogram. So, pH should be maintained okay, to a particular value. So, it should be neither low or neither high, like that. Okay, this about these chromatographs we are talking about. Since the samples is separate in the column, different peaks on the chromatogram corresponds to different components in the mixture. The chromatograms were obtained by separating a protein mixture using a ion exchange chromatography. The separation corresponding to the chromatogram, that is the A, was performed at a lower pH value than in B. This actually should look like this, pH should not write like this, it should be like this. pH should look like this, right. This shows that the operating conditions such as pH and temperature affect the output of the chromatography. Okay. If the pH changes, so your chromatograph will change. So, obviously, if the chromatogram change, efficiency, selectivity, everything will change. So, this used to be, so precise what are the desired value of the chromatogram, that is to be maintained, right. fourfold information is obtained from the chromatogram. What are the different components I am getting from the chromatogram? What are the different informations I am getting from this chromatogram? Right, already we have discussed, but let us jot down, right, one by one. The level of complexity of the sample is indicated by the number of peaks. How many, what is the complex mixtures that we can detect from this one. So, level of complexity of the sample is indicated by the number of peaks which appear. Qualitative information about the sample of composition is obtained by comparing peak positions with those of the standards. Okay. Qualitative information about the sample composition is obtained by comparing the peak positions with those of standards. Quantitative information regarding the relative concentrations, this is most important. So, we are measuring relative because the sample, if we are not absolute measuring, we are making the relative comparison, relative concentrations actually we are measuring in the gas chromatography, okay, because otherwise we cannot measure it, because we need the injections and it is only 10 microliter, that is the best. The smaller the sample, better is the detection. Sorry. Quantitative information regarding the relative concentration can be obtained from the peak and area comparison. Column performance can be checked by comparing with the standard outputs. Okay, this column performance also, because if I know the particular, suppose if I want to calibrate the column performance, I know the particular gas which actually we are injecting. Okay, so that time when unknown gas is coming, if I want to calibrate how the column actually working, so the column efficiency can also be can be known by looking at the chromatograph. So these are the four features which we will get from the gas chromatography. The most important thing is the relative, first of all, what are the different components of the gas present in the mixture. Second thing, the relative, this is the most primordial importance. Second thing is the relative concentrations of the gas or liquid or whatever it may be in the mixture. Okay. So, with this I come to the end of the lesson 36 of industrial instrumentation. Welcome to the lesson 37 of industrial instrumentations. In this lesson, we will study the pollution measurements. When we are talking of the pollution, basically we are talking of the environmental pollutions or the air pollutions or the type of gases, that means the carbon monoxide, nitrogen oxide, all these type of gases, how it is making the air polluted, and we must measure it, because the certain, if it crosses some limit, that is and it's not safe, it is hazardous for the human being. Pollution will be there, you cannot, in industrializations, there will be pollutions, you cannot avoid pollutions, you have to live with pollutions, but what is the level we must know, because if you stay in some forest, or there's obviously the pollution will be less, but if you live in a city, obviously there will be some pollutions because of the exhaust of the car and truck and all these things, burning of the fuels, burning of the waste, because the waste is a big problems in cities or metropolis. They cannot dump it, and usually they burn it, because that will reduce the volume of the waste. So that will cause the pollutions, the factories, the power stations, all these things will make the air polluted. Now we must know what is the concentrations of the different gases, and if it is within the safe limit, fine, otherwise you have to check it, and we have to warn. Our goal is to warn the public or the so that they will also know that what type of pollution they are going through, and what is the what should be the safe level of content. Now in some countries you will find that the forest fire, that also will cause the pollutions. Okay. Some countries where there is a where it like Australia, when it is very dry weather, when nitrogen monoxides or nitrogen dioxides in the sample reacts with ozone, which is produced by passing externally supplied O2 over UV lamp, part of the NO is oxidized to become a nitrogen dioxide, right. Part of NO2 generated in this is in the excited state. Excited state, so actually we are defining it by this one, please note. This phenomena is called the chemiluminescence. Actually, you see here. So, we are defining this NO2, this asterisk means it is in excited state. I am sorry, it is in excited state. NO2 asterisk, if it is excited state plus O2. So, it is NO2 excited state. It is liberating the, actually this will be H nu, I am sorry. This will be H nu, NO2, second equations if you see NO2 asterisk which goes to NO2 plus H nu, right. We can, this will be if I am, this will be H nu, right. So, the light will be emitted. So, above mentioned reaction is very fast and only NO is involved without almost any effect of the other coexistent gases. So, this also you should remember, because it should not react with the other gases, so the other concentration of other gases cannot be detected by that type of method. So, the phenomena is called the chemiluminescence. So, by this, so it is the nitrogen oxides react with ozone, it is making nitrogen dioxides which is in excited state, it will go back to the normal nitrogen dioxide. Now, you see we have then, now this is a color code of representations of AQI, we have given the color code representations, okay, that is anybody can understand. That means green means always friendly, as you know the environment, green environments we are talking about always is a good environment. So, we have given a color of green. So, 0 to 5 I mean AQI value. So, it is green color, it is good. 51 to 100 marginal moderate, we have yellow. Yellow, well, I cannot justify why it is yellow, it is some standard is to be followed. Obviously, the green means that our environment is green, always is better for us. Then we have 101 to 200 unhealthy, poor, I mean orange. Then we have a 201 to 300 AQI value, very unhealthy, very poor, which is considered red. Alert, red means always alert, and 301 plus is a critical. I mean there is no more for consumptions of the, I mean for that year is consumption for the human being or any living animals. So, these are the things which we have considered in this what we mean to by AQI. So, because if you give the color, because it is very difficult to remember all these numbers. So, instead of giving the numbers, we will measure this one, but once we define when to the public. So, we will give with some color. So, that green is better, yellow is okay, fine, orange is not that good, red is quite bad, and if the purple it is extremely bad, right. So, with this AQI color codings we can explain to the general public. So, what the color they should have in their particular area of residence or particular area where they are working. So, with this I come to the end the lesson 37 of industrial instrumentation.